We will now show that we need at least as many vectors to span a subspace than we can pick linear independent ones. Now put the vectors v that are linearly independent in A and the vectors w spanning the space V in a matrix B. Then the image of B, which is the column space of B, equals V. Yeah, since V is the span of W1, W2, and WQ. So since each of the vectors VI's, the VI's are all in V, they are in the image of the matrix B in particular. So there must be vectors U1 to UP that are mapped by B onto these vectors V1, V2 till VP. Yeah, so V1 is the image of U1 under multiplication by B, and V2 is B times U2, etc. until VP is the image of UP under multiplication by the matrix B. So this means that the VI's are linear combinations of columns of B. Now we may express the matrix A a little bit differently, because A equals the written in columns VI's equals now the matrix B times the concatenation of the columns UI. So we get B times U, where B is an N times Q matrix and U is a Q times P matrix. And notice that the kernel of the matrix U is included in the kernel of A. Yeah, whenever UX equals 0, then AX will be 0 as well. Also we know, since the columns of A are all linearly independent, that the kernel of A equals the 0 vector. Since the kernel of U is included in the kernel of A, the kernel of U must be the 0 vector as well. Now this can only hold if U has more rows than columns. Yeah, since U must be of full rank. So this can only hold if U has at least as many rows and it has columns. Which means that Q should at least be equal to P. And this is the end of the proof.